Okay, we are going to talk about the mean and standard deviation. So we have not described standard deviation yet. We have described mean. But this will kind of expand a little bit on means. Okay. Mean we know is the average of all of our data. Okay. So taking all of our data, summing it together, then dividing it by the amount of data sets that we have, boom, we get our average. Okay. The median is the middle number. Typically, if we want a resistant to outlier statistics, resistant to outliers, we're going to use a median. And this is not resistant to outliers. Example is this cartoon. It was clear why Jack was bragging about the mean height of his beanstalks rather than the median, because that one beanstalk was huge. It distorted the mean and distorted the true reflection of his data, which is that really we should have used the median since most of his beanstalks were short. Okay. There are two different means. Pretty much we will focus on one of these two. But in the first unit, we talked about how we have populations and how we would take samples of those populations. Okay. We talked about how populations produced parameters. Well, it turns out when I was talking about parameters, I was talking about a mean. Okay. And if we have all of our data in a population and find the average of whatever we're looking at within that population, doesn't matter whether you're talking about human beings or trees or beanstalks or ducks, if you find this data on that population and it's everybody that you're looking for, and you calculate your mean, you get this thing called a mu. It's like a U that's cursive, okay? And this is considered your parameter. It is the mean of your population. We discussed parameters now. We were just discussing averages. Now this is an X bar. We call this X bar. And this is our sample mean. So let's say instead of being able to poll all seniors in Lake Travis High School, I just took a sample by polling you guys, which is a sample of these seniors in high school, and I found an average of whatever your results were. That would be calculating an X bar, a sample mean. Okay, let's take an example of poverty rates in the eastern United States. Okay, this is all of the eastern United States, and if we wanted to talk about data from all of our eastern United States and find the average of it, we'd be finding the mean. Now, you were used to calculating the mean by taking the sum of your x's, we'll call them the x's, and dividing it by the number, and that gives you either the mu or the X bar. Okay? So you add them all up and you divide by the number that you have and you get that. I will tell you that sometimes it's hard to do that because if you make one mistake and you divide by the wrong number, you have to go back in and change that. So let's learn how to find the mean using our calculator. So in your calculator, you can enter in all this data into L1. Let's go ahead and do that. So stat edit. You can go ahead and clear the other data that you have in there and start and enter in all your data. And I will do it as well. And yes, this is in two columns, but since we're talking about the same thing, just poverty rates, we will put it all in one column. and I get 27 total states. Twenty-six total states. Good. Okay, if this is all of the states, this is our population, and we found an average, we'd find the parameter, this mu. To do that, go into stat again. Go to the right to calc, click on one var stats, press enter, and you see a bunch of stuff. You can kind of scroll down to see more stuff. Turns out this is where you could see a Q1, a median, and a Q3. You didn't have to graph things to see them. So in the future, if you want to find Q1, median, and Q3, you can use one var stats. But up at the top, and look, you see N. N is the amount of data points that we have. So we had 26 states that we entered in. That's the amount. We will be using N a lot. It's always amounts. Here they have X bar. They assume that what we're typing in is a sample, and they assume that we're calculating a sample mean. So they're just telling you that this is your sample mean. However, 8.90, 8 or just 8.91, this is what you would consider in this situation your population parameter. This is your mean of all of your eastern U.S. states' poverty rates. $8.91, that's up at the top, the X bar. Yes, sir. You got, okay, so if we got different values, we just typed in different values into our calculator. So check to see what you plugged in. This is the second time I've done this and I got the same value. Did anybody else get 8.907? Okay, so lots of us got that. So if you got a different value, you probably typed it in incorrectly, okay? Simple, okay? Now, I'm saying this is mu, but this is saying this is X bar. You should know that this is mu. This is going to be the population parameter. This is our average poverty rate, 8.91, and that's percent. Now, here's a great example of why we use samples instead of populations. Let's say it was impossible to get all of the states' poverty rates. Say some states did not produce their poverty rates, and say I could only take a sample. Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of these states, okay? I've just randomly sampled. Well, if you found the average of this sample, you would be finding the statistic or the X bar, the sample mean. So let's find the sample mean here. Stat, calculate, one variable statistics, my X bar 8.9, my sample size is 10, my min is 4.3, my first quartile is 6.7, my median is 8.4, my third quartile is 10.7, my max is 13.9. But in this situation, we found that my mean, my sample mean, my X bar is 8.9, okay? And that's great. My sample statistic is similar to my population parameter, which is what stats is really all about. Okay, samples can tell us things about populations. Great. All right, Well, describing the spread or variability, we talked about the range being a description of the spread, your max minus the min. We've also talked about the interquartile range as another way to describe that 50% of my data is between this and this. Well, now a new is standard deviation. And it's important to know that standard deviation is essentially, and what you're going to think about standard deviation is essentially it's kind of like the average distance that values fall from the mean. Essentially. It is not exactly that. It is not exactly the average distance values fall from the mean. That'd be the mean absolute deviation. We're not doing that. Standard deviation is a little bit different. It was shown back in the day to be a better use of describing populations. There are two things we will use for standard deviation. We will use this symbol, a sigma. This is for a population standard deviation, capital STDEV for population. And this small s we will use for our sample standard deviation. Okay? Essentially, it's the spread of our values. There's also something called variance. It's the standard deviation squared. It's actually what we use to find our standard deviation. We find our variance first, then we take the square root of it, and that's the standard deviation. Here are the formulas for the population standard deviation and the sample standard deviation. They are so similar to each other. And this doesn't make sense to you, but I'll just describe what it is. It is the square root pen, ink color, red. Nothing's working. It is the square root of the average of the deviations of your data from the mean, or the squared deviations of your data from the mean. My thing just stopped working. Okay, let's see how this works. Nope. We have derailed. Whoa. Let's see if this works. The key is I can't put my thumb down on the thing. I think I figured that out. All right, I think we're up. Good. Square root of the average of the squared deviations of your data from the mean. Okay, here's essentially what it means, okay, in a visual way. Sorry, did you get all that down? Square root of the average of the squared deviations of your data from the mean. Square deviations of your data from the mean. Okay? Essentially, what standard deviation is. Let's say we have a bunch of stars with a location on some axis, okay? And we can find the average placement of these stars, and it's right here. Okay, this is my average. Well, the standard deviation calculates the distance of all of these stars from the average. Okay, and it kind of averages those distances together. So we have a distance here of, say, like 1. This is a distance of, say, 2. This is 2. Let's say this is 3. This is 5. And it essentially averages those together. Okay? It doesn't do exactly that, but what it finds is just some measurements, some value. Let's use a different color like this, and it says, like, on kind of average, essentially, here, this distance, say 2.6 or something, this is the average of my spread from my mean. On average, we are kind of this far away for all my data from our mean. Does that kind of make sense? Okay, it's almost taking the distances. It's essentially, I can't say it's exactly what this is, but it's helpful to kind of see that. It's like taking our distances and averaging them together to see our average distance of all of our data points from the mean. So if I took like 1 plus 1 plus 2 plus 2 plus 5 plus 3 and then divide it by 1, 2, 3, 4, 5, 6, I would essentially get this. What we will be doing, though, is we'll be taking the square of this, squared, 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 adding those together, and then square rooting that, and then dividing it by the square root of the amount. It's a little bit more complicated than just an average, but I want to tell you that this is just what it means. It's just kind of how far away most of my data is from my mean on average, okay? Does that make sense? Nod your heads if that kind of makes sense. Okay, it's like the average distance from the mean. Okay. Here's how we calculate standard deviation. Well, you already did it for this value. We found this was 8.9, right? That was our sample mean. Look underneath, and you see this S of X, and you will find the standard deviation. So go into your calculators. You already had this last data set in. Screen, switch programs, boom. Your calculator does it for you. You see 2.97. You can say that on average, most of your data is within 2.97% of 8.9. Okay? If you add 2.97 to 8.9, you get a value. Subtract that, you could say, like, you know, a lot of your data is there. We'll find out that about 50% of our data will be within that range. We'll find when we add 2 standard deviations and we multiply that S of X by 2, we'll find that 95% of our data is going to be within the range of 2 standard deviations away from our mean. Okay? We'll talk about that more. But that is essentially the spread. Okay? We can think about 8.9 plus 2.97 and 8.9 plus minus 2.97, and it gives us kind of an idea of how spread out most of our data is. Okay? Well, you also can find the population if you had all of this in and you would look at this. This would be the population standard deviation. Now, it's different, and I'll tell you why it's different in a second. If I looked at this, if this was the population of my 10 things, my population standard deviation would be 2.81. But that is not the correct population standard deviation for this data right here, because this is not the data that we plugged in. There are differences between the two formula, as we can see right here. Essentially, this is just your data value. This is your mean. And this is the amount to give you your average. This is the same thing. It's your value. This is your mean. And we take our average, instead of dividing by the amount, we subtract 1 from it. Well, the reason why we subtract 1 from it is because if we took a sample of maybe just 3 of these stars, and we found our sample mean was this, well, our distances are going to be kind of less. You'd have less distances from our mean. Maybe this is 1, this is like 3, and this is also 3. Well, if I took the average of this, 3 plus 1 plus 3, and that would be 7, and divide it by 3, I would get a value that's going to be a little bit smaller than I need it to be. So when I divide by n minus 1, so kind of like the average essentially divided by n minus 1, it's going to be bigger than if I had the average divided by n. And it's going to be a better approximation than this. And I could get really into it, but I don't think we need to get too much into it. But that's the difference. If we take samples, we'll have to get a bigger value to do a better job of approximating my population standard deviation. Okay? So sample standard deviation, we do n minus 1. Population standard deviation, we do n. Because the samples have less values in it, we need the kind of spread to be a little bit larger to mimic the population. Okay, so that's essentially what it is, but let's actually figure out how to calculate the standard deviation. We're going to do it with a table. I'm going to kind of show you by hand how it's done, and then we're just going to be using our calculator from here on out. Okay? Here's what we do. We start with, a sample data set. So this is a sample data set. I have 72, 88, 96, and 100. Now, you won't have to calculate the sample standard deviation by hand, okay? You're going to be able to use your calculator. Once you guys enter in those 5 data points into L1, and you find the sample standard deviation. I'll do it as well. I'll show you how it's done by hand so you can see what's going on. Stat, calculate, 1 variable statistics, boom. If this was a population, we'd say it's 10.723. Instead, we know this is a sample data set, so we're going to be using this S of X. We found that our mean was 89, and this sample standard deviation is 12.38, okay? That kind of shows us the spread of our data compared to the mean of 89. Well, here's what they do. It's essentially you take all of your data points, you subtract them from the mean, 89, to find the distance. Now, the distance can be negative or positive in this case, because if you take 72, subtract it from 89, you got a distance of negative 17. Well, we want all those distances to be positive. So what they do is they square all the values to make them a positive, and then they'll go ahead and take the square root of the sum of these values divided by the amount of these values minus 1. So they'll take this 460, they'll add them all together, they'll divide it by 4 minus 1, and then they'll square root it. It's a complicated calculation. It is not as simple as if I just taught you the average distance from the mean. It's a little bit more in depth, but you just really have to understand what it means. It's thought of as an average distance from the mean, okay? On average, your data is kind of about 12.38 units away from 89. So if you looked at kind of 89, add 12.3, subtract 12.3, would be kind of where the rest of our data is located. Does that make sense? Nod your heads if we're paying attention, okay? Okay. On average, the individual data values are about 12 units away from the mean. That's essentially what it means. Okay. we could calculate a bunch of means and a bunch of standard deviations for these 5 data sets. But it's as simple as just plugging it into your calculator. Why don't you guys do this one and this one for me? And I'll do the other 2. Do the first 3 actually, and then we will do the 4th just by looking at our data and seeing what's going on. Is this for which one? The middle one, so 90, 90, 100, 110, 110. Found the mean was 100, that makes sense. And the standard deviation S of X is 10. Did anybody do the top one yet? What did you get, Mr. Holtz? Interesting. Did we do the 3rd one, Mr. Riley? Nice. Entering multiple lists. I like it. We got 150. Look at what's going on here, and let's see if it makes sense to you. We have data that's 100, 100, 100, 100, 100. It means 100, right? Because all the data, all 5 data is 100. Well, the standard deviation, or the average away from the mean, well, all of these are right on the mean. So the standard deviation is 0, because there's no distance of all your data points from the mean. Let's look at the second one. We go 90, 90, 100, 110, 110. Okay? We are starting to spread out some of our data. Okay? We still have the same mean, it's 100. But notice our standard deviation is a value. On average, we are 10 units away from the mean. Notice how it ends up being exactly 10 in this situation. Sometimes it won't be that obvious. Then our 3rd set of data. We start to spread out even more. Our mean's 100, our standard deviation grows even though our mean is staying the same because my data values are spreading out. Now, looking at our next one, 90, 90, 100, 110, and 320. This value, pretty large, right? Probably an outlier. Do you think outliers are going to affect our standard deviation? Do you think I'm going to have a bigger value than 50 here? What do you think, Mr. Englander? Yeah, I think so too. Why don't you guys figure it out? We spread out more, our standard deviation should go up because on average, maybe you can think about our distances from the mean being larger. What do you get, Ms. Nebergich? $99. Okay? And our mean was 142. Okay. It's unfortunate that it's not 100 again, but because we have more spread in our data, our standard deviation value is going to increase. Okay? Even though our mean is not changing. Our shape of a graph will determine what we are going to be using. This is a uniform with our data just all consistent. This is going to be symmetric. This is also going to be symmetric. this is going to be a skewed data set. What we will find is that a lot of our data is close to each other in this last one, except for this outlier. So if you almost excluded this outlier, you could say, yeah, most of your data is clumped together. Because of that, we don't like to use standard deviation for skewed data sets. Because a standard deviation, like a mean, is a non-resistant statistic. It will be affected by outliers. Okay? We will be using standard deviation for symmetric distributions without outliers. And that is the next thing. If you are symmetrically distributed, you will be using standard deviation because the mean is going to be the same as the median. Standard deviation will be good. However, if your data is skewed, you use the median and your interquartile range because those are resistant. I can't spell resistant. Please write this down. This is very important. These are resistant to outliers. Standard deviation is not resistant to outliers. If you have outliers, we're not going to want to use standard deviation to talk about spread. We'll use interquartile range typically. If we have outliers, we don't want to talk about the mean. Typically, we'll talk about the median because the outliers will affect our data more than they should. Okay? Now, let's plug in 10, 12, 12, 15, 18. And do your one variable stats. Go. We get our mean is 13.4. We find if we scroll down, our median is 12. We can find our range by taking our max minus our min is 8. We find our standard deviation is 3.13, and our variance, which we haven't really talked about, but that would be the sum of the x squared is 937. Divided by 10 would be 937, okay? Now, if I change my data by adding 5, and I went to 15, 17, 17, 20, 23, figure out our information for this new data set. Does the mean change? Does the median change? Does the range change? Does the standard deviation change? The mean is now 18.4. Well, I take 13.4 and add 5, I get 18.4. The median, you go down, is 17. I take 12, I add 5, I get 17. These two things, we add 5 to. However, the range of my data and my standard deviation remains the same because all of my data has moved up proportionally. Standard deviation and range remains the same. We will add 5 to all of our values. Last thing. What if we multiplied all of my data by 3? And I would have gotten 30, 36, 36, 45, and 18 times 3, 4, 2, 54. Is that right? Find your mean, your median, and your range and your standard deviation for that third data set. Ready, set, go. 30, 36, 36, 45, 54. We get 40.2 for our mean. Our median pops up to 36. Our range between the max and the min is now 24, and our standard deviation ends up being 9.39. What happened? Well, it turns out not only is the mean going to be affected, you're going to multiply by 3, and the median you're going to multiply by 3, but also the range and the standard deviation get spread out, because when you multiply, you are not moving things proportionally. And our data values are going to be spread out more than our data values here. So this is very important. If you add values, and this is the last thing you need to write down, if we add or multiply, our center is going to change, add or multiply. But our spread, our standard deviation, will only be affected by multiplying our data. I don't like how they say here. I like the previous one, but the previous one's too crazy.
Good morning. These are today's announcements. Attention students.
And let me show you an example of that.
If you are portal in Schoology for TSI, they should report to E203 at this time.
Hey Cavaliers, do you remember being a Buccaneer? Hudson Bend is not the same without you. Join us this Thursday at 5:15 to celebrate our first annual Back to the Bend Spirit Week to show off your Hudson Bend alumni spirit. We will recognize you at the HB volleyball game. Can't wait to see you.
Lakeside has talent. Now is the time to show off the fabulous talent at Lakeside.
All right, last thing, just as an example right up here, if we change by adding, we will not change the spread, but we will change the center. If we change by multiplying, we will change both the spread and the center. Let me give you your homework, and you guys can work on that during CAP time.
There is still time to get your gold Cap Against Cancer t-shirts for the designated Gold Out Day. The proceeds go towards pediatric cancer awareness.